Join the conversation.
You're with Cape Talk.
Thanks so much. It's just after 9:30. It is Friday. It's time now for the Naked Scientist. Dr. Chris Smith answers your questions related to science and natural history. Dr. Chris Smith, nice talking to you again. How are you
likewise.
doing?
Welcome back. Happy birthday for last week. We missed you.
Thank you. Appreciate it. But we jump straight into it then. Zuki calling from Big Bay. Good morning, Zuki. How are you?
I'm good, thanks, Lisa. How are you?
I'm okay. You asking a question that hits very close to home for me. Go ahead. Ask Dr. Chris.
Okay. Good morning, Dr. Chris.
Morning.
I wanted to know, people who cannot pronounce the letter R, especially the hard like R, is it because there's a physical problem with their tongue, or is it how the sound translates, or is it because of practice? What causes that?
The proper word is rhoticism.
Zuki, it's very close to home for me because, as you said, rhoticism. I cannot for the life of me, and I've been for speech therapy, I cannot deliberately, purposely pronounce and roll the letter R. It's almost impossible for me. Chris?
I can't roll my R's at all. There are some people who will be able to make their tongue sort of vibrate to get those really rich I just can't do that. I can say R, no problem. I can say words beginning with R, like Robert and Richard and robust and robot. I don't have a problem with that, but I cannot roll R's. This suggests to me that rhoticism, which is the thing that we're talking about, the inability to say R's without it coming out differently, it's probably a movement-related thing. It's the ability to form the right tongue contortion. There's a tongue twister for you. Not quite rhoticism, though, that enables you to make those sounds. I don't know why it happens to discreetly affect some people and not others. And it seems to be a sort of learned movement, doesn't it? When you make these sounds and then you learn to speak that way. But I'm going to do a bit more probing into this. I don't know physically whether it is actually the inability to make the movement or something else going on. I suspect it is, but I will come back next week with a bit more clarification. And thank you very much for the excellent question.
Is it also, I don't know how geography plays into the physiology of your mouth and how you make movements. Here in the Western Cape, where I live, and in South Africa, the vast majority of people, particularly in Cape Town, can say the letter R, and with that rolling sound. Also, if you were to go to parts of Spain, Latin America, people, part of their language have that rolling, vibrating R's. Does geography, could it also play a part in one's physiology?
Well, it's certainly true that certain languages do not involve making certain tongue movements and sounds in certain orders, which means that when people come to those languages from a non-native background, they can struggle. And a really good example of this is, I went to school with a Japanese guy, and he could make an R sound, no problem. I said to him, say R, and he said R, no problem. If you then get him to say the word rugby, he would say lugby. And then you'd say, well, say ugby, and he could go ugby. But he couldn't run the two together because he would go lugby. And it's because he intuitively had learned to speak in such a way in order to form Japanese patterns of speech. Because when we're speaking, speech is tongue movements and airflow. Those tongue movements form a very, very tightly coordinated sequence of movements. And in the same way that just playing tennis, playing football, playing an instrument is a tightly coordinated sequence of movements, you learn and practice and rehearse and become really very good at doing them. And so when you then try to play an instrument badly, you can't do it because your brain is overriding it. And so if you have learned to speak a certain way because of the dialects in your area, because of the sorts of word and speech patterns that happen with the accent you use, or the language and the words that you use, how your language is crafted, then there can be some languages which are totally counterintuitive to the pattern of movements that you have learned to make naturally all your life. So unsurprisingly, you trip over them. And I find this when I am doing Naked Scientist radio programs, you get somebody's name, which is of a certain part of the world, which you just find really hard to say, because the sequence of sounds is not at all natural to your language. And as a result, when you try and say it fluidly and smoothly, unless you rehearse it a lot first, which, we try and do that. But sometimes if you're on a live program, you can't do that. And you find yourself stumbling over it. And it's not like you're trying to insult the person because you can't say the name. You genuinely cannot get your tongue around the words. And it's because they are totally unfamiliar in sequence. Now, that's why I think that this is down to a pattern of movements, although why it happens to some people and not others don't know. It might be a combination of the anatomy as well as everything else going on, which means that some people find it harder to make certain patterns of tongue movements in certain positions that will give them those sounds. But I'm going to take that away and have a look and see if I can find out a bit more.
Thank you so much. Let's go to Ross in Thornton. How are you doing, Ross?
Yeah, man, doing well. I came from the same origins as Chris Smith. And arriving in South Africa, I learned to roll my R's, man. So from matters of language to matters of the heart, I recently underwent an MRI scan and lay in a long tube, and my heart was examined, which was totally painless, except for a sort of warm feeling in my back. But I was told to lie still and not to move even a millimeter. It was okay for about half an hour, but after that I was battling to keep still, and my back was aching. And the whole process took about 2 hours. So by the end of 2 hours, I wasn't feeling too good. Surely it's possible with the software that's invented for GPS, a sort of adaptation could be made so that a patient in the scanner could move a bit and not have backache for an hour and a half like I did, so that, that point of reference could be kept so that the radiologist would be okay and not messing up his photographs.
Hi, Ross. Yes, you're right. It's very unpleasant when you're stuck in that tunnel for a really long period of time because it's quite claustrophobic and it's boring. And also your body is programmed to want to move around, because the reason that we don't get pressure sores by continuously compressing the same bit of our body and therefore stopping blood flowing properly through that tissue when we're doing anything is because we're constantly on the move. And even when we're asleep, we're continuously on the move to avoid applying too much pressure to certain parts of our body. So it goes against the grain when you're stuck in a scanner like that not to move. Now, the reason they have to get you to stay absolutely rigidly still is because what they're trying to image is tissue that is moving. And the way in which you image tissue that is moving is by making reference to tissue that isn't. Because then you can work out what is moving, what's moving naturally and where it's going, and you can subtract out some of the noise. And there are really very good algorithms for doing this, and it has got exceptionally good, which is how you're able to have MRIs of soft tissues that are continuously expanding and contracting with blood pulsing through them. But there are limits. And so by keeping the bony landmarks that move much less, like ribs and your backbone vertebrae, other tissues, rock solid in position, you can use them as a reference, and the software can try to correct for some of those anomalies. But remember also, we're trying to see things with some of these scans which are down at very tiny scales, and therefore you're very close to what the noise is, the natural movements and the artifacts and the error signals which are in there as well. So to make sure the signal can stay as pure and crystal clear as possible, you have to minimise the noise that you're adding to the system, and that means trying to stay, unfortunately, as still as you absolutely can.
Thanks so much for that, Ross. Much easier off the tongue, James in Simonstown. Good morning.
Oh, good morning. And good morning, Chris. I recently learned, to my surprise, that calcium is a metal, and metals are defined just as something that conducts electricity and heat. Could you go more into how we define metals and liquids, etc.? That does seem an odd definition for me.
If you're familiar with the periodic table, James, that we used to have up in all the chemistry classrooms and things like that, where you basically got this nearly 120 different chemicals, which we know, individual elements, all differing by how big their nucleus is. You could draw a line across the board about 3/4 of the way across and say everything to the left of that line is a metal, everything to the right is a non-metal. The properties of the two are very, very different. And metals, characteristically, if you could see inside a metal with a really powerful microscope that could see individual atoms, for example, what you would see in a metal is you'd have islands of positives, which are the nuclei of the atoms, where all the protons and the neutrons are, and washing around them would be this sea of electrons. negative charge. And the reason that metals are really good conductors of electricity and of heat is because they are this sea of electrons which are all mobile. And so an atom can basically borrow an electron off the atom next door because there'll be another one coming along to replace it. And so in that way, the metal is not electrically charged, but it does have all these mobile electrons that will enable it to conduct electricity. And that's why we use metals as good conductors. And yes, calcium is a metal. It's in group 2 of the periodic table. It's similar chemically to magnesium in many respects. But when metals react and they go through reactions, chemical reactions, so they're no longer the metal, the metallic element, they become what are called ions. And when metals react to make ions, they lose electrons. So in the outer part of the atom are electrons that are being held onto less well by the metal than electrons closer to the nucleus. So it's possible when they react for them to give away these extra electrons, and if you give away negative charges, you become positive. So when calcium reacts in that way, so if you took metallic calcium and you burned it in air, it would react with the oxygen in the air, and it would give the electrons it wants to get rid of. It's got 2 spare electrons in calcium. It would give them to oxygen in the air because oxygen has gaps for 2 electrons. This means the calcium becomes calcium 2 plus charged ions, and the oxygen becomes minus. And the 2 stick together because one's plus and one's minus, which holds them together as lime, calcium oxide, which you can then slake with water, and it becomes calcium hydroxide, slaked lime. But the calcium, when it's dissolved in water, is going around as these charged particles, calcium ions, and that's what makes water hard. And if you live in, say, Johannesburg, for example, you know all about hard water because of all the dolomitic limestone, which is around the city, for example. And those dissolved calcium ions, when they end up in your water heater or your kettle and everything else, they can then degrade from the dissolved form into a hard calcium carbonate rock form again, and that's where you see visible calcium deposits in your kettle.
Let me ask a follow-up there, Chris. Then how then do water softeners work? I know a couple of people who have lucky enough to have dishwashers, and they're always saying, they need to get salt or to soften the water. How does that work?
The hardness in water is caused by calcium ions chiefly. So that would be dissolved forms of calcium, which are formed when rain falls on calcium-rich soils and rocks, because rain is a bit acidic. It's got carbonic and also sulfurous acid in it. And this means that you get a form of dissolved calcium called calcium bicarbonate, which is soluble. This goes down the pipes to your house, and when it goes into your dishwasher or whatever, because there is calcium in the water, when we use soap or detergents are long oily chains with a charged bit on the end, and the oily bit sticks into the grease and the charged bit associates with the water, and in that way it pulls the grease, which doesn't want to mix with water, into the water and makes it dissolve, and that's how you clean your pots and pans. But calcium, because it's small and it's a strong positive charge, grabs hold of the charged bit on the detergent molecule, and because calcium is got 2 pluses on it, it can grab hold of 2 detergent molecules. And what you end up with is a calcium sandwiched between 2 oily bits, which then makes scum on the water. So when you run the water through a water softener, you have to replace the calcium with something that can't do that. So what you do is you use sodium salt. And the water softener contains a resin which is covered in sodium. And when the hard water with the calcium goes through the softener, the sodium swaps places with the calcium because the calcium likes binding onto the resin quite well. So what you do is you pop off 2 sodiums and replace it with 1 calcium because sodium is only 1 plus. So you end up with water that's a bit salty. But sodium, because it's only got 1 plus, can only grab hold of 1 of the fat chains. So it doesn't make scum in the same way, and your water is now considered softened, and you can't use as much soap not to clean up your dishes anymore.
Let's go to 1 or 2 voice notes.
Good morning, it's Monet from Stellenbosch. There's been so many studies on how a normal childbirth, a natural childbirth, and a C-section has so many different, especially long-term effects to a baby and to a human being. What is the actual reasoning and understanding around that?
Go ahead, Chris.
The answer to this, let's first of all ask, well, what are the differences in outcomes for babies that pop out the normal way versus babies that are born by caesarean section? And let's first of all preface that by saying that caesarean section, under certain circumstances, is absolutely critical and saves lots of lives. So this is not in any way dissing caesarean sections. These are very valuable procedures which save lives under the right circumstances. But what we have seen in recent years is a shift towards being born by convenience. So the rates of caesarean section in some countries have climbed very considerably, and this cannot be explained on the basis of safety. This is explained on the basis of babies being born by convenience, which means we must therefore ask, is this the best outcome for babies that could otherwise have been born the normal way? And the evidence is that there are long-term health consequences if you have a caesarean delivery, and there can be long-term health consequences for mum, and there can be long-term health consequences for the baby. The question really dwells on the baby, so let's focus on that. The difference between a natural birth and a caesarean birth, obviously you're being squeezed out of the birth canal when you're being born the normal way. This can be a traumatic procedure, but it has a number of benefits for the baby. One of them is that you squeeze all of the muck out of the lungs and things, which can mean that babies tend to breathe well from the minute they're born. But the most important one from the consideration of long-term health appears to be what else the baby is exposed to on the way out of the body. And as it comes out through the birth canal, it's being born into a part of the body which is extremely mucky. It is a sea or an ocean of bacteria, muck. And as one person put it to me once, the baby's first taste of life is a mouthful of muck. It's mum's muck. And we're talking about vaginal organisms, we're talking about skin flora and bugs that live on the skin, we're talking about the colorectal tract, so you're talking about fecal organisms, all of which are going into that baby. And you'd think, wow, that sounds pretty horrendous. Why do we want that? We spend our lives trying to stay clean, not dirty. But actually, that's probably the most important meal, if you can look upon it that way, that baby ever gets, because the bacteria that are coming into the baby via those roots are the right microorganisms for a baby with the genetics that it has, because it shares its genes with its mum that lives in that environment, and her environment, her diet, and therefore the diet and environment the baby will be inheriting is the same as mum's. And so those organisms are ideal for the baby's genetics, and they're ideal for the future environment and diet it will be exposed to. And those organisms take up residence throughout the gut very quickly. If you compare babies that are born by caesarean, where you're hoiking a baby out from a sterile environment, which the uterus is, into the outside world, and then plonking the baby into a cot and then doing various procedures, etc., that baby's colonization with microorganisms is very different and occurs at a different rate, and with initial bacteria of different types coming in compared with the types that would come into a baby born by caesarean. And that means that the pattern through which the microbiome, the family of microorganisms that populate the intestines and the skin and all the different parts of that baby, follow a different trajectory in the baby born naturally compared to the baby which is born by caesarean section. And that does appear to have, at least in some cases, long-term health impacts, because the risk of allergy is higher in babies that are born by caesarean section. The risk of longer-term bowel complications, bowel diseases, diarrheal diseases is much higher in babies born by caesarean section. Now, this is an average, this is not an absolute, so there will be babies born that way, absolutely fine. There will be other babies that are born the natural way that will have those problems, but on average, there is a shift, and that shift appears to have quite a long-term impact on the colonization of the guts, and therefore the long-term health of babies that are born by caesarean versus the natural route. You can also see similar impacts through breastfeeding, for example, which is why doctors, nurses, midwives who are familiar with the birth process will advise, to the greatest extent possible, you should have as natural a birth as possible. That doesn't mean it has to be uncomfortable or painful or dangerous. It means that you should, as much as possible, have as natural a birth as possible, because that does appear to be associated with the best long-term health outcome for your baby. But obviously, if you're in an extreme circumstance, then you may need a caesarean section to save your life or your baby's life, and you absolutely shouldn't not do that if that's the case.
Let's go to Blanche in Strand. Thank you so much for your patience. Ian in Elgin, I see you. Good morning, Blanche. How are you?
Hi, good morning, Lester. Thanks for a great program. I am sorry for going back to the pronunciation of the letter L. But, in my work in certain South and Eastern countries, my name was pronounced as Branch. And, Malawi is an example, but also in Eastern countries. So your comment on, perhaps geographical influence or differentiation on how we pronounce letters holds water. In the beginning I found it strange, but I accepted that, I was Branch in certain countries in Southern and Eastern Africa. So very, very interesting. It would be useful to find out more about, the causation of, why it's pronounced differently. But thanks for a great program.
You're very right. I was in Malawi and I was called Resta. You just unlocked a memory for me. But Chris is going to do some digging and he'll come back next week with probably a more definitive answer. But
yeah,
Ian,
I'm going to do a bit of research.
Ian, how are you doing?
I'm doing well, thank you.
What's your question?
My question is, why does there seem to be a difference in long-term memory and short-term memory? And people who are getting old seem to remember things from their youth, but forget things that happened last week.
Hi, and the reason is because the mechanism of memory storage differs between the two. The way in which we store long-term memories is in different parts of the brain in the connections between nerve cells. These are called synapses, and you can both strengthen and weaken the connections between nerve cells, and so we encode information as groups or clusters or networks of nerve cells that fire off in response to certain inputs or stimuli. That happens through a process called consolidation of a memory. So when you have an experience and you then translate that experience into long-term memory, you are writing it into a changed pattern of activity and connectivity in certain nerve subsets in certain parts of the brain. And different parts of the brain store different sorts of information. So in your superior temporal gyrus, which is the temporal lobe of the brain roughly adjacent to where your ear is, the upper part of that, you have an area that stores faces. And you have nerve cells there which are dedicated to storing memories of people's faces. Other bits of the brain will store other things, movements, for example. But short-term memory is very much hinged on a structure called the hippocampus. You have two of those on each side of the brain, also in the temporal lobe. And in this area, there appears to be circuitry that encodes short-term memory. It's also very important for learning how to find your way around and remember mental maps of the world around you. But this structure is critical for holding information in short-term memory, but also then initiating the process of memory formation and translation into long-term memory. When we age, because we don't lose the connectivity all over the brain, you don't lose your memories of days gone by, but we tend to have a less good mechanism for capturing short-term information and then translating it into consolidated long-term memory. So the hippocampus does shrink as we get older, and it loses its ability to be as efficient at storing short-term information and then locking that information in, which is why characteristically people who develop age-related dementing illnesses, which are very common, and over the age of 80, maybe as many as 1 person in 5 to 1 person in 4 may show signs of this. The erosion of the volume of the hippocampus means they're less good at capturing that information and storing it. So you tend to see a decrement in short-term memory, but preservation, at least relatively speaking, and at least initially, of longer-term past experiences.
Malcolm in Rondebosch, you'll be our final caller for this morning. How are you doing?
I'm doing well, thank you.
What's your question?
So the question is really about whether we should be talking about gravity as such, because we now understand that what we perceive as gravity is actually due to the curvature of space-time. So just wondering what Chris thinks about that.
Chris?
When Isaac Newton first came up with the concept of gravity, he obviously hadn't got the insights that Einstein added to the formula years later. and he envisaged that massive objects have this notional thing he called gravity, which enabled them to attract one another. And Newtonian mechanics enabled us to explain to a very good approximation how the universe worked. But when Einstein came along and began to look at these things, there were certain things that didn't quite work. At certain scales and extremes, Newton didn't work. And so Einstein set about putting that right and said, well, we have to come up with a concept of gravity, and this is his theories of relativity, that explain why things work at all scales and what gravity is. Now, we haven't found a grand unified theory yet where we can actually say how all of these different entities are interlinked. But what we can say is that you can regard space as a fabric called space-time, a concept, because time and space are deformable by mass. So if you put something massive in space, it deforms or bends space. And it bends space to such an extreme in the case of a black hole that not even light can come out. So we think of gravity as not so much a function of if there's something special about the mass. The mass does something to this entity that is space-time and deforms it in such a way that then other things which are causing deformations try to roll together, almost like two balls placed on a fabric sheet where they both bend the sheet down, but the heavier one would bend the sheet more and the lighter one would roll towards it. That's gravitational attraction. Both would move towards each other a bit, but the smaller one would move a lot more than the bigger one. But that's sort of as far as we've got at the moment, because we are still looking for ways to tie all these things together and work out exactly how these forces all interlink. We think they probably do in some way, but we don't exactly know.
Dr. Chris Smith, the Naked Scientist, I am really, really, really looking forward to next week if you can answer our questions on rotatism.
I'll do my best, Resta.
I'm looking forward to that. Thanks so much. Dr. Chris Smith,
Take care.
Joins us again
Bye-bye.
next week.